Really? I pushed play and nothing happened. $18. Oh, I wonder how loud that is. Okay. Five, 6, 7, 8, 9, 10. Oh, jeez. Oh, jeez. It's weird. It has number 7 here. 5, 7. But I'm just going to download it and see what it looks like. Yeah, you know what? I'm not going to download any of these. I'll just download these. It's so weird. Like, why have they been different? Is it gonna open it or what? Wow, I don't know why it's labeled as this 5.7. It appears to be relevant to the question of 5.18, so it's just labeled incorrectly. Number 18, weight of a typical American male, mean of 180, standard deviation of 30, 1.92% of all American males weigh more than I do. Oh my gosh. No way. No way. No way. They just basically gave you the answers. They just gave them to you. They gave you the answers. You know, I wonder if that's because the professor didn't provide a video. It would have been so much easier for him to make the video than to do this. I don't know, maybe that's how it was originally, but man, this is easy. They made it way too easy. The mean is 180. Thank goodness I'm under the mean, but probably my BMI is terrible. It's probably way above average. Oh man. Oh man. First one. Suppose 91.92% of all American males weigh more than I weigh. So, wait, what fraction of American males weigh more than 225 pounds? What fraction weigh more than a certain number? So that's pretty easy. I've done this stuff before. Yeah, I know. It tells me the answer. I'm just trying to understand it, okay? Because I need to take a test over this in a couple days. But, why did they give you the answers? What? Dude. Stop. Okay. I'm trying to understand. What is the percent more than 120, 225? We got that. Yeah. And we're doing 1 minus because we're trying to find more than this. So x more than 225. And then we have mean, which is B4, which is 180. And standard deviation, which they gave us as 30. And we want true. They typed 1, but I'll say true. It gives you the same result. Oh, jeez. What percent of American males weigh more than 225 pounds? Very few. Actually, it's very few. So, yeah. Not very low percentage there. B, what we're trying to figure out is how much do I weigh? So, they gave you the facts that his weight is in the what percentile? 90? Well, no. Because this many of males weigh more than he weighs. Therefore, he is in the 100 minus this percentile. And see? 1 minus this. That's what I said. See? Me is smart. Jeez. So now we're looking for a percent. That was awesome. That was awesome. We're trying to find his weight. So we're doing the reverse of the thing we did before. We were given the percentile. We want to find the result. And that means we use the inverse function. And they told us that he is in the 1 minus this percentile. So we say that percentile, the mean and standard deviation. So equals norm in. Hello, everybody? Hello? What the? Oh. Hold up. You know what's funny? I think it would give me the same result. I'm just gonna... They're being dumb. It will give me the same answer. So, interestingly, they're using the old version of it, but I'll use the new version. Norm.b. And so it's going to be 1 minus this, comma, mean, comma, standard deviation. So it matches. So his weight is 138. Yeah, that's way less than me. That was funny. That was way less than me. Can I please stop saying that? Stop. So, new weight. Well, if I weighed 20 more pounds, what percentile would I be in? So, that was funny. Equals this plus 20. There's like a flea, like flying in front of my face constantly. Like, come on. Why? Just why, dude? So norm dot dist this comma what percent of what would the percentile be? So if you're just trying to find what the percentile is, what percent of people weigh more than this? What percent of people weigh less than this is the percentile by itself. So yeah. Norm dist B60, B4, B5, true. So his new percentile, his old percentile was some other thing. But yeah. So there you go. We're already done with the question. And so we'll rename that one. We'll rename it to 518. It was for number 5. It was for number 18. They basically just gave you the answer, but I'm trying to understand it so that I can take the test. So yeah. Okay. 1 out of 10 is complete. The first one is extremely easy. So just hope the rest of them are that easy. That was funny, 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 that was funny. That was funny, that was funny, that was funny, that was funny. Okay, number 26. We'll just download it from here, because it's going to be more reliable that way. So this would, we're trying to do 26. We're going to assume that this is 26. And then open it up. Huh. So this looks like it won't be too bad. This stinking fly keeps doing stuff. Wow, look at this. So what are we doing right now? We're going to be trying to do number 26. Fast food restaurants. There's part A through D. That matches. Oh, what? It only has part A through C. But maybe it's still the same question. There are hamburgers and chicken sandwiches. The demand for hamburgers has a mean of 313 and a standard deviation of 57. The demand for chicken sandwiches is 93. Standard deviation of 22. How many hamburgers must the restaurant stock to be 98% sure of not running out on a given day? So that's part A. Part B, answer part A for chicken sandwiches. Yes. Part C, if the restaurant stocks 400 hamburgers and 150 chicken sandwiches for its given day, what is the probability that it will run out of hamburgers or chicken sandwiches on that day? So I think it kind of gives you a hint of how to do that question there. So very interesting. What's the probability we'll have hamburgers or chicken sandwiches or both? Man, that's a complicated one right there. Oh geez, this is a hard question. Whew. So 98% sure of not running out. All right. Well, so basically, 90% of the time, 98% of the time, it will be less than this number. So we will do that. So it will be equal norm dot dist less than a number. I believe we're supposed to do this instead. 0.98, 313, and 57. Hamburgers, that was for A, hamburgers. So 430. So what we'll do is say 431 hamburgers right there, just so we can round it up. But we also show how I got to that number. And then how? So will be equals norm.inv probability 98, mean 93, standard deviation 22, and so 139 chicken sandwiches. And so that's pretty easy. Now part C is the hard one. Now that was funny. Okay, let's think about this. Okay, so we said that we should be safe and have 431 and 139, but they said, let's go 400. Oh, wait, what? Why did they go with 150 here? We got an answer of 138. 93, 22. We got 431 and 139. So it's weird. They kind of overstocked their chicken sandwiches, but understocked their hamburgers. So let's see. Given day, what is the probability that we'll run out of hamburgers or chicken sandwiches? Right. This or this. Either it will be above 400, the probability that it will be above 400 hamburgers, and then the probability that it will be above 150 chicken sandwiches. Alright, so this is the probability. I love how they use PR instead of P. The probability of stock out of at least one I love how these are mislabeled. It's mislabeled, dude. What the heck? So 1 minus... So what the probability of stocking a stock out of at least one equals 1 minus the probability of no stock out of either equals 1 minus the probability of no stock out of hamburgers multiplied probability of no stock out of chicken sandwiches. Okay. That's complicated. No, it's not. I'm just dumb. And I sounded dumb when I said that. The probability of stocking out at least one is 1 minus the inverse. What's the opposite of stocking out at least one? At least one. The opposite of that is you didn't stock out either one. What's the opposite? Now, what is the probability of not stocking out of either one? It's the probability of not stocking out of hamburgers multiplied by the probability of not stocking out of chicken sandwiches. So it's nice that they gave you a hint. So here we go. We're trying to figure out a probability. No, wait. Whoa. No. That's not where we're typing it. Where are we going to type this? Right here? Here? It's what is the probability it will run out of hamburgers or chicken sandwiches or both? So the probability of stocking out of at least one. So equals norm equals 1 minus, we're going to go parenthesis, norm dot dist. So what is the probability of stocking out? What is the probability of you did not stock out of hamburgers? That means the number is gonna be, I hate everything. I hate this question. I'm going to put 400 because it's less than 400. It's less than 400. I'm going to use the number 400. Too bad for you if you think that's incorrect. $400. What is the mean of hamburgers? Is this. The standard deviation is this. And then we're going to go true. Then we're going to go minus. Oh, we're going to have to do another parenthesis. Parenthesis. A parenthesis. One minus this times norm dot dist. The probability of stocking out, so we're going to go 150 or not stocking out, rather 150 says their probability so what is your chance? Probability will run out of both. No, it says it'll run out of either one. Either one. Interestingly, the answer is 6.8%. So, why is the independence assumption part C probably not realistic? I'll put the answer right here. If they run out of one of those two options, then customers are more likely to get the other option. For example, if I want a hamburger but they have run out, then I would probably get a chicken sandwich. Using a more realistic assumption, do you think the probability would increase or decrease? That would increase the amount of chicken sandwiches that are ordered, which would increase the chance of running out of chicken sandwiches. Wait, hold on a second. The probability that you wouldn't run out of either one. Oh, come on, wait. Probability that you would run out of one of the two things. Isn't that awesome? I've done with this question. So we're done with that. We're done with 2 out of 10. After 40 minutes, it's taking an average of 20 minutes to do each question, interestingly. This is funny, this is funny, this is funny, this is funny. This is funny. Let's do math. They are down by 3 scores. Wait, hold up. Yes. They are down by 3 scores. Because, yeah. So we have finished question 18 and 26. So now we have to do 28. Number 28. Right. Part A through C, number 28. 28. Oh, crap. Let's go to the next section. Here we are. 28. Space vehicles. One original system and n-1 backup systems. Each of these systems functions independently of the others with a probability of 9.98. This shuttle component functions successfully provided that at least one of the n systems functions properly. There's a certain number of systems. Each one has a probability of functioning of 9.98. Find the probability that it will function successfully if n equals 2. Don't you just do like 0.98 squared? Like 0.98 times 0.98? Wait, no, I'm stupid. Never mind. That's not it. That's not it. Dumb idiot. Okay, think again, buddy. You're oh man, so it's like a binomial. We have 2 test runs. The probability of success for each one is 0.98. So I think that's what we have to do. It's like a binomial function or something like that. Probably gonna double check that one. Probably. Just Rob. Oh man. Let's just be sure here that we're not messing up. probability of 0 successful. Getting ahead is, there's 3 attempts, probability of that x is 0. You could do k is the number of successes, the probability of getting this many successes with this many trials of this probability. What is cumulative or whatever? This doesn't feel quite analogous. $58 100 number of trials, 58 successes. The probability of getting 58 successes in 100 trials. No more than this, less than this, at least this. So, okay, so here's the thing. False means get exactly this number. True means get this number or less. That's what true means. Okay? Number of trials, probability. So let's see. In our case, we're going to do true trials. The probability is 0.98. What's the probability that you have a yes success? Wait just a second here. The number of successful trials. Okay, so basically, what's the probability of getting 2 successes? Because there are 2 trials, and we want 2 successes. We want 2 successes, and the probability of success is 0.98. So I think I got this. And we want it to be more than 2. No, we want it to exactly be 2. We want it to have exactly 2 successes. Obviously, it can't be more than 2 because we only did 2. So it's going to be false for the. It's not going to be less than 2. It's going to be. It's not going to be 2 or less. It's going to be exactly 2. So the way to do A is it's going to be equal to binom.dist. The number of successes is 2. The number of trials is 2. The probability is 0.98. And it's false because equal that. What's the probability that you have 2 trials of 98% each, and they will both be a success? Isn't it 0.98 times 0.98? Like pretty much if you did 0.98 times 0.98, you would get the answer. I'm not stupid. Wait, hold on a second. Wait just a second here. Wait just a sec. I don't think this is right. Wait, undo. I think it's right. Oh, this is great. I'm confused. Because If it's two duplicated systems, doesn't that mean that there are three systems totally? Oh, come on. Why is this so confusing? Okay, I get it. It's n minus one backup system. So there's actually one backup system, so that's a number of systems of two. So yes. So like I'm sure this is right. Like number of successes is 2 because there's two systems. They both succeed. Oh, you know what? I think I'm wrong. Because only one of them has to succeed. You don't need both of them to succeed. You only need one to succeed because it will function if one of them succeeds. So, all you actually need a probability of you have one success, 2 trials, 98% success rate, and false. So actually, there you go. You have a... I just realized. You want the probability of either 1 or 2 successes, which means you do 1 minus this. You do 1 minus... You want true... I think... Okay, this is weird. This is... Did I get the same answer? The probability of at least this many is 1 minus this true. Oh, and you do... Oh my god. Oh, dude, what the heck? At least 59 successes. This is so confusing. Because I think now you have to do 0 greater than 0 because... Oh, this is why I want a video at home. This is more than 0 successes, which is weird because you could end up with like 0.1. Probability of having more than one, of having one success, at least one success, because at least 59 is 58, greater than 65 is 65 here. At least... Oh, yeah, but you can't have 0.1 successes. This makes no sense. We want one success. of the probability of having at least one success, you do 1 minus that number. Do they even talk about that in their explanations of this stuff? Because, like, please. I don't think they really... I hate this textbook because it doesn't explain that point well enough. It doesn't explain it at all. It just doesn't explain it. This, okay, you're doing 1 minus something. What's the probability that it's going to be 0 or less? But what we want is the probability that's going to be 0 or more. But no, we want it to be 1 or more. We want it to be 1 or more successes. We don't want a 0.1 success. We want a 1 success. Do they even do fractions? The probability that you have at least 1 success. According to their example, the probability of having at least n successes is you put 1 minus that number. I mean, that number minus 1. Like, what? They don't even explain why. They literally... Oh, why is it so hard? Oh, it's not hard. It's just that the textbook is the textbook. I had the same problem in the project that I did earlier. I had the same exact problem. Probability of having more than 0 successes. What if I put a fraction? I'm going to be right back. Let's keep in case she needs this one. What a fun time, everybody. Stop. Man, I hate this question. I just hate this textbook. I don't hate the question. I hate the textbook for not explaining this question well enough because, like, dude, man. Yeah, just man. Probably of having at least 400. Wait, 0? What? What on earth? Probability. I love how they do blah -1. They don't explain, they never explain it. They never explain the -1 or whatever. But I'm hoping that's correct. Like, you just do, you want one success, so you do 1 minus 1. It's like, basically, what's the probability of getting more than 0 successes? That's what we're getting right now. It's like, oh, it's slow killer. No. Probability of having more than 0. Well, that would work, but like, does it even tell you if it's discrete? You can't have half of success, obviously. So this is correct. It's the probability of having more than 0 successes. There's 2 trials. So that should be right. Now, what's the probability it functions successfully if n equals 4? So it's basically the same thing as before. 1 minus this number of successes. So it's like having more than 0 successes, trials of 4, probability of 0.98 true. Oh, come on, what? It's literally getting 100% correct. I mean, it should be correct. The probability that you're going to have more than 0 successes if you have 4 systems and they all have a 98% chance of being. Now, if you have your decimal point out as far as you can possibly get it, it will eventually looky. Like, eventually you will end up with that. Like, look at how successful it is with just 2. That's insanely successful. Like, is that even right? You have 2 systems, they both have a 98% chance of succeeding. So the probability that at least one is going to succeed is even higher than 98%. And then 4, my God, it's like basically 100%. It's like the chances of all 4 of them not succeeding is just ridiculous. It's like 0.02 to the power of 4. Well,
What's the maximum number of systems that must be incorporated to ensure at least a 0.9999 probability of successful operation? Okay, so we want jeez, oh jeez. What about the inverse stuff? Give me an example of inverse. There's no way there. Why would you do trial and error? No. Just no. Just no. Wait. There's no way that we have to use trial and error to do that question. There's no way. To get number 68, I hate this. You seriously have to use trial and error? This is ridiculous. This is ridiculous. There's no actual formula. There is one. They're just being dumb and being like, let's use an inefficient method, and now let's use an efficient method. Probability that x is less than or equal to k is more than or equal to 95%. The binomial inverse function returns a value. It returns the smallest possible value such that the probability that x is less than or equal to the value the probability that you have less than or equal to this many successes, less than or equal to? Oh no. Like what they were trying to do. I messed up. That was funny.